This is part 2 of our How to Make a Solar Array video series. In this video, we're going to be going through the quantum mechanics and theory of how solar panels turn solar energy into electrical energy. So let's get into it. So our question reads, how do solar panels convert solar energy into electrical energy? Well, in a short answer, light photons hit the electrons on the solar array and excite them into higher energy states. Then a positive-negative junction, or PN junction, harnesses these electrons and guides their flow, which is the current we see in a solar array circuit. After some energy loss through heat loss in the wire, all the electrical energy is dumped into the battery, and the electrons turn back to their previous energy state.
The photoelectric effect explains how a solar panel harnesses the solar energy of the sun and turns it into electrical energy. It explains how electrons are given energy and how they respond to said energy. The first step of this process is a light photon hitting a piece of metal. When all the solar energy is absorbed by the electrons on the surface of the metal, they excite. This means that they jump up to a higher energy state and leave behind an empty spot in the valence shell they originated from. It's very important to recognize that an electron will only be excited if it's charged with the exact amount of energy needed to make a jump to a new state. As in quantum mechanics, electrons can only exist in specific states. These electrons can only return to their original state by releasing the proper amount of energy or decaying back into their relaxed position.
This band gap directly comes into play immediately in our solar panel through the material that is used to build it. We use a semiconductor, and unlike a conductor which is metal, these things have a much larger band gap. In a Bohr model, this would look like that each of the rings, there is a larger gap between them almost. So for the electron to move between them, it would need a larger charge or a longer amount of time to decay back. This gives you more control and allows you to have more precise amounts of energy move between your areas.
The easiest way to understand how positive-negative junctions, or PN junctions, work is by using an analogy. For example, if a house was in a storm, the rain would beat off of the roof in a random way and the water would be lost. However, if gutters were to be installed, the water would be collected and directed into a single area for future use.
So in terms of what actually happens, here we can see our solar panel and there's photons hitting these electrons, these little blue dots that are on our solar panel. Now on an atomic level, here's a Bohr model so we can see what actually happens. These photons hit these electrons and they excite them and go to these higher energy levels, which is this further away ring. And in the absence of a PN junction, as time goes on, this electron will eventually just relax and return to its original energy state. So the exact same thing happens when there is a PN junction in terms of the first couple steps, except now when a photon hits an electron and it goes to a higher energy state, the electric field that the PN junction creates actually gives the electron a place to go, so it is then carried away in its field. A commonly asked question though is how come electrons in higher energy states are carried away by the PN junction's electric field and not the ones in lower energy states? And the reason for this is because the electrons that are in lower energy states, it means they're closer to the nucleus, and the pull of the nucleus is stronger than the pull of the electric field. So as the electron moves further away, this pull becomes weaker and the electric field from the PN junction will overtake the strength of the pull from the nucleus and will subsequently take the electron away.
A PN junction is a combination of two materials to create an electric current. It uses a p-type material and an n-type material connected to force the movement of electrons. These materials connect at something called the depletion zone, which is when the electrons of each material bind together to force an electric current. While both materials are electrically neutral, together they create an electric charge in one direction.
It helps to think of a PN junction like a little hill. So electrons can roll down the hill, as you could see, but they cannot go back up. It's not possible. And so with a PN junction, it allows you to basically push your electrons in one direction without them going back the other way.
So the electrical path begins in these crystalline grids that are placed all over the panel. The photoelectric effect causes the electrons in here to move around and the PN junction pulls them into the conductors. Now that the electrons have reached the conductors, they want to head towards the troughs. The troughs are bigger metallic lines placed all across the panel, and the troughs lead them towards the wiring that's on the back of the panel. Once they've reached the wiring, they head towards the battery, and the battery is where they unload all their electricity and head back to their original spot.
This has been part 2 of our Templeton Solar Array YouTube series. Please leave a like and comment, and check back on our YouTube channel for part 3.